So what is the state of the art when it comes to wireless communication and networks? What kind of transformations will we see due to AI and machine learning in particular? So we're talking faster rates, more devices, and different kinds of devices, especially as they gain more and more autonomy. What are the implications for all of these changes? Introduce yourself and talk a little bit about your expertise.
Sure. So my name is Walid Saad, and I'm a professor of electrical and computer engineering at Virginia Tech. My research is essentially at the intersection of wireless communication networks and machine learning or artificial intelligence. And we look at both like how do you fundamentally build the two systems like communications and AI, as well as a lot of applications. So in the past, things like, of course, video streaming and so on, but then going to new applications of communications, like for instance, the metaverse, extended reality, of course, vehicular and drones and all sorts of things along those lines.
So we're already living with well-developed wireless communication technology that I think is probably mysterious to a lot of people, actually. So I wanted to just start there with like our current system, how that works, because it's pretty amazing, actually. The fact that there's thousands of cell phones in my area and this cell towers can communicate directly with me without interference.
Sure. Yeah, I'll try to keep it as simple as possible. So I mean, at the very basic level, so communication is all about the idea of trying to convey a certain information at one location in space to another location, right? And historically, communication. I mean, we used to use smoke signals, right, and flags and things of that sort. And I mean, fundamentally, the concept is still the same, but now we want to carry that information over electromagnetic waves and at the end of the day, it's all about how do you, so to speak, put that information on a communication signal or on a frequency, right? So that is carried over a wave. So at the end, every communication signal, you have a transmitter and a receiver. And the whole goal of communication is being able to recover at the receiver what you sent from the transmitter, right? And recover it as correctly as possible. So with what we call minimal bit error rate. So the ones and zeros I send, I want them to appear the same way they were sent at a remote location. And so that's like what we call a single link, right? One transmitter, one receiver. Once you get to a network, the whole idea is about how do you organize these resources that you have. So when you communicate over, let's say what we call now 5G or 4G, or the more broader term is what we call cellular networks, right? So it's a wireless cellular network. So the idea is that we want to try to organize information over the resources we use to carry information over electromagnetic waves. And those resources are really time or frequency and space in some sense, right? So in which region of space do I use which frequency, for example? So why do cellular systems work very well? Because they kind of leverage the idea that one of the negatives, if you wish, of communicating over wireless is that power of a signal decays with distance, right? So you can only reach so much. But at the same time, that's a positive because if there's a certain frequency I want to use, I can reuse it a little bit further away because there will be no interference because the power is small, right? So we need to maximize how much we can use within the region of interest in some sense, and we can reuse frequencies in another region. So there are many technologies, right? Trying to, which frequency times chunk I should give to which device at which point, and in which region. And there are so many things to kind of like do there. And another reason why things work really well, especially end of 4G, like I'll get back to what a G means, right, in a moment. But let's say end of what we used to call LTE and the beginning of what now is 5G, is this idea of being able to use more antennas on these base station towers, right? So there's a regime called what we call massive MIMO, which means MIMO is multiple input, multiple output, which means in some sense we're packing so many antennas at a certain base station. That kind of means that I'm sending the signal in different ways, right? So I can combat obstacles, I can combat the attenuation that might happen. So we call it diversity. I mean, in the sense like I'm sending diverse signals, and at the point, again, making it very simple is that one of them will reach there, right? One of them will arrive to the receiver with sufficient information to be decoded, and that's one of them reasons why things work well. And the other reason is organizing the frequency times in a useful way. And another benefit on why having multiple antennas is good is because you can actually now direct the power of a signal towards a certain device. And this is something we call beamforming. So I can actually send, like, focus your signal on the device communicating with me and kind of eliminate as much as possible what's outside that. Of course, there's no way we can eliminate what we call interference completely. At the end, I have colleagues who spend their lifetime just trying to manage interference in different ways. And interference is the point when you have two signals using the same frequency, basically colliding at a given receiver. In summary, there's, at the link level, there's ways we can do to represent the signal to be able to recover it well. At a network level, we need to organize our resources, and we need to basically leverage technologies like multiple antenna systems to basically do better in some sense.
Yeah, so the cell phone towers know more or less where your phone is and can just point directly at you then.
Yes, I mean, there is what we call a little bit like a handshake procedure that happens initially. Like, we try to understand, where the device is, it's active, it's going to transmit. You kind of raise your hand in some sense. I want to transmit now. I mean, and you talk back and forth. But it's done so well that it's very seamless nowadays. As a user, you don't feel it that much. I don't know if in the past you remember when you used to have a cell phone and you're driving in a car and you have your radio on. At some point, you hear some sort of, like, there's a kind of static on your radio. That was because this phone was moving from one base station tower to another. That still happens, but the static is much smaller. You don't probably hear it, or because you don't listen to radio. It's either one of the two.
Yeah, listen to it on your phone now. Yeah.
Yeah.
Talked about that it's kind of an advantage in some sense that the power dissipates. So does that mean as we're creating these shorter and shorter wavelengths with more and more towers, does that mean that it's going to enable more devices on the network as well? Is that part of the reason? Or I'm sure there's some other reasons as well.
That's a great question. I'll go back a little bit to this power decays with distance. I kind of cut it a little bit short. Because it decays with distance, we can, mathematically at least, represent a communication network as a series of hexagonal cells, and that's why it's called cellular networks. The hexagons are just mathematical representation. In real world, when you get, like, measurements from, let's say, AT&T and so on, they don't look anything like a hexagon. But the hexagon turns out to be very useful. I mean, to kind of understand a little bit how the system works. But now, with that said, there's this trend of, because one of the most valuable resources in communication is what we call the spectrum, which is really the frequency. You have only so much, and that is regulated. I mean, in the US, it's regulated by the FCC. For example, AT&T and so on, they bid for certain spectrum chunks and so on. And going back a little bit to your question, I mean, I'm just saying that because every few years, when the spectrum becomes more and more congested, we start thinking of higher frequency bands. Now, the higher you go in frequency, the smaller your coverage area. That's good and bad, because it's good going higher in frequency because that means you can give more bits per second. Some of the promises of 5G were allegedly supposed to come from higher frequencies, but I'll get back to that maybe later on why that didn't happen. That makes the cells shorter, which means you can cover less with a single cell. That brought forward a few years back this concept of, we said we want to densify the network, meaning deploy as many of those small cells everywhere. Unfortunately, that turned out to be more expensive than what people has foreseen, right? So that didn't really happen, at least at the scale that was foreseen. But the point was kind of to what you said, like, we shorten the frequency, then with this idea of beamforming, then we can better manage everything, and then interference becomes anyway smaller, and we have, like, all these large number of small cells. We call them millimeter wave frequencies, and those are actually the same frequencies that they use for detecting you at the airport, right? When you do, the scanning, because they penetrate. I mean, they can image the body and so on. But unfortunately, millimeter wave for 5G did not work well because of two reasons. One, densifying turned out to be expensive, and second, while these higher frequencies give you higher bits per second, unfortunately, they're a little bit brittle in the sense that if there's a little bit of a blockage, like now, if you're not using millimeter wave and you put your hand on your phone, nothing happens really. You still can talk. With millimeter wave, it's a little bit, I mean, to take it extreme, it's a little bit of a 0 and 100 gigabit per second. Either you get nothing because it's blocked, or you really get a lot of data because you have a good, what we call line of sight. So you get view of the base station. So because of these two reasons, specifically when you're mobile, right, when you're moving, when you're static, there are some millimeter wave base station that have been deployed for like static access, where the user is relatively not moving that much. But when you're mobile, it doesn't work, at least yet, it doesn't work that well.
To get everyone on the same page, make sure we know this. Just explain what higher frequencies do, because we're already sending the signal at the speed of light. So why does the higher frequency mean faster signal transfer?
Oh, sure. I mean, there's a couple of reasons, actually. It doesn't automatically mean that, but one of the reasons is that those frequencies, those higher frequencies, are simply not that used, right? So we have more available of them, so we can allocate more of them to a single device. That helps a lot because traditionally these cellular communications have been done at frequencies up until 4G and even 5G up to 6 gigahertz, right? So those are like our sweet spot. Unfortunately, those are very crowded because everyone wants to use them, right? You know, there are so many applications for them. And in the past, there used to be like some interesting example, like in the US, there were frequencies at the time where wireless was not that popular that were actually sold for very little to like TV, right? You know, UHF and VHF. I don't know how many of your viewers will remember those. And then at some point in time, those become golden, right? So those owning them will be able to either sell them for very high price or to actually, you know, let people pay to use them, right? Because they became a little bit more important. So that's one reason, which is the availability. The second reason is when you go higher in frequencies, you can build smaller antennas, which means you can pack more antennas in a small region. And the more antennas we can have, we talked about massive MIMO a little bit earlier, the better we can do massive MIMO, the better we can, you know, point to you, right? I mean, again, this doesn't work exactly yet as such, but if, as an example, we think that at higher frequencies, we can do what we call pencil beamforming, which is it's as small as a pencil. It can just directly go to your sensor, right? And again, that has challenges. It hasn't worked as effectively as it should. But those are practical challenges that people eventually will overcome. But that's the second reason why we can, you know, give you more bits per second.
So what kind of things are engineering factors that we're worried about when we kind of step up to these different kinds of they're really different kinds of signals, right?
Yeah, I think this issue of blockage is an issue, right? What we really call it blockage. So the signal is highly susceptible to blockage, which means in some sense it's not very stable. So in ensuring that stability, again, stability is not the technical term we use, but ensuring that line of sight, right? Guaranteeing line of sight is really one of the biggest challenges. And there are different ways to try and do it. In some sense, again, making it simple, at the lower frequencies, the problem is interference because I don't have a lot of bands available. So I have to reuse a lot of the same frequencies. So interference remains an issue. At higher frequencies, interference, at least theoretically, I can combat it by doing pencil beamforming because then I'm just beamforming. There's theoretically no interference, even though the beams can overlap, but that's a low probability. The challenge becomes how stable they are. So we have these two regimes, lower frequencies, very stable, but cannot give me high frequency because of interference and the scarcity of the spectrum. High frequency, I have a lot of spectrum, not a lot of people are using it, but I still cannot establish stable enough links to give you, you know, the promised theoretical, at least, gains.
There's a lot of speculation still because, you know, this is new technology. Everyone's trying to figure out the direction to go with it. I've seen like people are thinking of new building materials that can just bounce the signal better, or maybe every cell phone is a sender and receiver, and you're just chaining all the devices out there, chaining the signal together, and they're sending and receiving everything. I think it's pretty cool. People are at least thinking of all these things.
Yeah, I mean, I could comment a bit about this idea of like bouncing things. So there's this concept that we call the reconfigurable intelligent surface. Think of it like a mirror, right? Like where we can plug it in different places. It could be really an magnetically active wall, right? That is really has this communication capabilities, which can allow the signal to bounce off. But there are also a lot of challenges with that. I'm not a hardware person, but with the advances in metamaterials, I think people have done significant advanced in that respect. But there are also even simple issues like, because you have on these reconfigurable surfaces, they're passive in the sense they're just a dumb mirror put there, right? Even being able to know what we call channel estimation, even being able to know what the communication channel will be at every one of those small antennas on that big surface is not a very trivial problem. But that's a promising technology. I think people have done a lot of work on it on the academic side. There are less industry activity there still because, again, it's not very easy to deploy in the field. But that's one possibility. I'm not sure if it's the one that's going to make it eventually, but that's one possibility.
So maybe this is unfair since you just said you're not a hardware guy, but I'm curious if is there a fundamental new technology in hardware that is enabling this, or is just kind of an iteration of the previous and it's a new generation because it has all these different problems and implications?
Yeah, I think being able to build those surfaces, it's a combination of the two, right? I mean, some of the things we learned from classical communication, they still apply because before we used to have relays. I mean, and we still have relays. There's something called a relay node. The difference is that now you want to pack a lot of antennas next to each other and you want to make a large surface. And my understanding is that there are challenges in building those. And it seems metamaterial is one direction, but there are actually classical approaches that are used to build classical transmitters and receivers that some people have been toying with and have shown promise, where you can put what we call this phased antenna arrays and just put them next to each other. I mean, there are ways to do it in a cost-effective manner. I think cost is important, right? Because if you want to build this RIS, what we call reconfigurable intelligent service, and it's more expensive than putting a base station at the base station tower, then I'll put the base station tower, right? Because the base station tower can give me more capabilities. Why would I kind of trade it off for this mirror if it's not cheap enough? And there were some other like related ideas. I mean, if I remember well, it was Ericsson. I don't know if they deployed those effectively or not. Either Ericsson or Nokia, one of the two Scandinavian vendors. They used to have these like straps. You can just like the straps you put when the band-aids, so on. You can put them on walls, and they are electromagnetically active, and they are antennas.
Hmm.
And those were cheap. But I haven't followed what happened with them. They were a hype at some point, but I don't really know where they're at now with those.
That's pretty good for me for understanding sort of the fundamental technology. I want to get into the applications because I know you write a lot about that. So I thought about this as I watched a movie recently where they're talking about the electrification of America, creating the grid. And basically what kicked it off was Edison invented the light bulb, and now all of a sudden there's a thing that everyone wants in their homes. And so that was the technology that like enabled the demand for this infrastructure. And then of course, once the electrical grid was built, it enabled our modern world, basically everything that we see today. So I was wondering first, if we can draw an analogy there, if there's some technology we currently have that people want to use this faster networks for.
And I would say there's the light bulb and the electrical grid for us in telecommunications that happened maybe in the late 90s, right? When people wanted to be able to communicate where they're on the go, and we couldn't do that with the old phones, right? Which are really cables, and you had to be at home, and that's where things kicked off because at the time. Wireless was amazing, right? Now I can be in my car and I could actually take a call, and that didn't happen before. And the main really driver was to be able to speak to one another, right? It's really voice. Voice was the driver. And back when I was like in the maybe early 2000s, even like 2005 and so on, people were saying, okay, wireless is done because I can speak with you. I mean, voice is perfect, right? We have no problems anymore. And what else can I do with this phone? I mean, okay, we can send messages. SMS was very popular, and that also worked really well. So people were saying, this area is gone. There's nothing to do. It's a commodity now. There's nothing that we can do. And then came the so-called iPhone, and that changed significantly because no one at the time thought, oh, I can do all these cool apps on a phone, and the network was not ready for that. There was a storm of things. I mean, I don't remember the exact code, but one of our operators, I think it was Verizon, they were saying, okay, the iPhone kicked off a storm of traffic on our networks. What should we do? There's a supply and demand curve that I actually use in one of my classes, which shows that, this demand for wireless, basically for communication, was kind of saturated. And then you can see a certain point in 2007, everything went up and no one, I always ask the students, guess why, right? In the past, they used to guess. Now, they probably, for them, the iPhone is a commodity already, so they
Mhm.
don't really think. But it was the iPhone, right? And then you can do all these applications. I would say today, we don't have a certain like application which is not possible to do, in the sense like we really, really need to have faster networks to do it. But the philosophy is that if we give you faster networks, someone very intelligent out there will come up with something extremely amazing, and the iPhone being case in point, right? Who would have thought at the time? Again, I was working at an operator at the time, was not in academia. And we were just saying, okay, what are we doing with this network? It works really well. Yeah, we fix things every few now and then, they happen. That's maintenance. But in terms of research, maybe we shouldn't do anything. And then all of a sudden that happened. So, but the exciting opportunities lie ahead in things like virtual reality, because COVID taught us that we may need to do these things like Zoom we're doing now more often, and being able to do it in a way with a more interaction is useful. So things like being able to be with you in the room without being with you in the room. That requires, of course, advances in VR and extended reality technology, but to be able to do it, you need communication, and being able to, so to speak, create a second world that is digital where we can interact in it is very meaningful. Of course, I'm not, again, when we say metaverse, that might sound a little bit pejorative because of Meta's involvement in it and what they
Mhm.
sell it as. But if we think about it only as, a few applications where people can do like meetings, or people who are in remote work, I think the future of work presents a tremendous opportunity for using the networks more, in some sense, and all sorts of things that are autonomy, right? Autonomous factories, and things of that sort, which
Mhm.
can work today, but we can do better.
That's right that you mentioned the iPhone. I remember that time as well because feel like I'm naturally skeptical of these things. I remember my friend getting one of those. Like, what do you need that for? You can already call and text people. Like, and then I remember the transformation. So I definitely need to check my skepticism there, and that's why I wanted somewhere like you to kind of like give me some encouragement for the future here. Um, okay, so you write a lot about AI and machine learning as well. Is there a technology there that this will enable, or that's pretty speculative at this point? And then does it work in the reverse too? Because I saw like part of enabling this kind of network might be utilizing AI technology as well, right? To understand the signals and convert them in
Yeah,
that.
there is a two-way street there. Broadly speaking, we can talk about AI for networks and networks for AI, right? So these are two
Okay.
different. I'll start with the second because you asked about it first. So networks for AI. The point being that AI eventually, of course, there's hype and there's real things, but eventually there will be applications which are using artificial intelligence. I mean, think of a team of drones, right, trying to communicate back and forth, things of that sort. And those applications will involve usually more than one device, and they may need to speak to each other, right? And that's where wireless comes in, right? So it's a use case for communication networks. It's a new use case. It's a bit different because for example, it's instead of emphasizing high rates, some of those AI applications want you to be extremely reliable, right? Because they
Mm,
don't send a lot of data. Maybe they send a little bit of their AI model and send it to someone else. They may not send a lot of data, and that's something we've seen in the Internet of Things with 5G. But with
mm,
AI applications, they may be different. So it's a very interesting use case where we were among the first to actually think a bit about that, and we talked about something called joint learning and communication, where I want my AI to be as accurate as possible and my communication to be as accurate as possible because they're interrelated. Because if I send you some of part of my neural network and you receive it in error, that doesn't only mean that the communication was bad. It means that whatever prediction you're gonna do may be bad as well because you received something in error. That's not the fault of machine learning in that case. It's the fault of the communication network that was not sufficiently reliable. So there are anything that requires interconnectivity of multiple AI-powered systems that needs communication eventually. So you need to look at it. Even this idea of like VR and so on, because a lot of these things, when you're in a virtual environment, a lot of like your avatar, for example, that's an AI model. This avatar should be you, right? You should be synchronized. And to be
mm,
synchronized, it means that the delay or the latency should be near zero. And that's a challenge for communication networks, right? And latency, we spoke a lot about rate, but latency is the big driver for like recent wireless technologies. Now, the flip side of the coin. So AI for wireless is a very interesting area. When I did my PhD, when I used to go to talks and say, oh, we can use some sort of machine learning or artificial intelligence, not specifically ML, people would laugh at me, say, oh, this will never work, haha, communication doesn't need it. But we came to realize that no, we need it. I mean, now 6G networks, they call them AI native, which means theoretically, at least, many of the processes we used to do through, like, let's say, optimization algorithms or like heuristic algorithms may be done with AI, and it may be more effective. Now, what can it help us? So we talked about this unstable environment. That's an area where it can help us, because if I can predict well how the obstacles will come and go, so to speak, then I can potentially prepare the network to, there will be a blockage there, maybe do something with it. So I can do these simple things at the very least. Currently, when people talk about AI native, at least if we want to be on the humble side, even these things like how do we transform information into the symbols we send over the channel. Now it's done using algorithms that date maybe 50 years ago, and they work really well. I mean, there's nothing to complain there. But Nokia, for example, have done some work where they showed, well, with some machine learning, we can come up with even better ones, right? And that's good. Embedding ML helps you really do better. And think about it, like communication technologies like antennas and all the things we talked about, we're going to still push them forward. But eventually there's a cap, because there's a physical limit, right? There's a physics will stop you. Now, you cannot overcome physics in any way, but with machine learning or AI, you may be able to be more intelligent in a way that you will reduce how close you are to the physical limits, and kind of do more with less in some sense, right? So I can kind of do more with less, and then these constraints, while they're still there, they're hard constraints, no one can break them. We cannot break the laws of physics, but with intelligent way of, like, managing resources and so on, I can actually give you better connectivity and still abide by those laws of physics, somewhat circumventing those in some sense. So I think these are the two, AI for networks, networks for AI.
Yeah, lots of data used in both
Yeah.
cases. Yeah, yeah.
Yeah.
So I was wondering especially for something like self-driving cars and whatever else you can imagine, like the avatars that you were talking about, that's going to require a lot of computing as well. Do you envision those being done on the device, whatever app you're running, or is that going to be like a network computer where you're just going to be running the app, sending the information, and then it's going to be computed in somewhere else at Apple or, some other station?
I think it has to be a combination of both, because the eternal trade-off has been, if you compute locally, you're faster, but you have limited computing power. If you compute at a cloud or a faraway location, you can use as much computing power as you want, but you have latency. And if it's a self-driving car, you need to be able to tell it to stop as fast as you can. So you cannot keep going back and forth. I think a combination of the two. But this is where AI also comes into the picture, in the sense, like, if you have a central location where you can do these all very strong, intelligent predictions, and then think of that as a teacher, and then teach those small students on what they should do in certain use cases, and the edge devices, basically the other devices, the glass and the smartphone. And then if they need you, they would ask you again, right? So kind of reduce the back and forth. So going from sending everything to question and answers in some sense,
Okay.
and that could be pretty interesting. But just a small tangent there, or not specifically a tangent, but when we talked about 6G, and I think we were one of the first to talk about 6G, we were very specific to call it a wireless system, not a wireless communication system, because we think it can give at least 4 services now, not just communication. It can give you computing, because you have all these towers and so on out there. Why not use them to compute? It can give you energy. There are some research on this radio frequency charging small things, right? I mean, I'm not gonna charge your Tesla battery. Maybe that's too much.
Mhm.
But the fourth one being what we call sensing, or another term for the same thing is called imaging, meaning like you can, through the communication signal, not only communicate but also basically image the environment. Know that your head is turning this way, and this sensing helps actually overcome the stability issues as well, because now, even if the link is blocked for communication, I may be able to recover, there's an obstacle there. that's an exciting area, and that becomes more possible with high frequencies because we talked about that before. The higher you are in the frequency, the more you can actually do a more accurate sensing, and that's useful.
So some of my skepticism comes from like the Internet of Things. Like I know that was hyped up for a while. You're gonna be like your watch is gonna talk to your phone, to your microwave, and your refrigerator, and everything's gonna be communicating at all times. And I don't know, I haven't really seen that come to fruition in the way it was imagined. I was wondering if there's a reason for that, or just people weren't interested, or if there's some sort of fundamental thing with the technology there that didn't really work out.
I think the bigger reason is that I think some of the applications were not that realistic. Anyway, I mean, just I don't think there was a business case for some of the applications, right? So things
Okay.
didn't, from a business perspective. From a technology perspective, we did make headways. I would say for Internet of Things, the focus were on two things I mentioned, which were delay, latency, and what
Mhm.
we call reliability. Now, latency, 5G did really well in latency, not as low as we wanted it to be, but it's still pretty low. I think, if I'm not mistaken, again, sometimes the numbers vary, but I think they were able to achieve 5 milliseconds in the field, which is really, really good. Not too far from the 1 millisecond people were envisioning. But the other one, which is reliability, reliability was thought to be this idea that I want to make sure that with 99.999%, which we call the five nines, the link is, I mean, the transmission is successful, which turned out to be more challenging than thought to be. I may be mistaken, but I haven't seen practical deployments of 5G where they achieved the reliability they claimed they would. I've seen lab tests, but in the field, I don't think they achieved that. And that somewhat contributed a little bit to not the full deployment of the IoT. But I would think, and this is speculation, that if the business case was there, they would have still found a way to to make it work. But I feel the business case was not there. I mean, even self-driving cars, they're nice, and I mean, we can talk about them, and I'm sure in the future we'll have something close to them. But I think the more realistic use case would be human-driven cars with some automated assistance, right? Not a fully self-driven cars.
Okay, yeah. Could you talk about that a little bit and talk about what you think that might look like, why self-driving is going to be difficult, and why a 6G network might help?
So I think one of the issues with self-driving cars, which is maybe not completely a technology issue, is that there are a lot of risks involved, right? I mean,
Hmm.
it's not like, these metaverse and so on. If it doesn't work, your avatar fails, nothing happened, that's fine. You'll be frustrated for a few minutes, but then sure, no problem. But if you have a self-driving car that goes off a cliff, then that's a problem. And that's not specifically communication only, right? I mean, the communication network may work, but there are so many things that may fail at the same time, right? The AI that is powering it may fail. The brakes may fail. There are so many things, and there are actually a little bit of like existential questions that face these self-driving cars. Like if you're a human and you have two options, I can either hit a pedestrian or hit a deer, and then you obviously will swerve to the deer. You have only these two options. But maybe the optimal way, I mean, the technologically better way is to just ram the pedestrian in that case. And if you're relying solely on an AI algorithm, it might just do that. I mean, there are ethical and guardrails that are not very obvious to me, at least how you would put them. I mean, you can put cases, but it's hard to envision those. So I think
Hmm.
there are these issues with it. I mean, in some cases, for example, I've seen campuses run self-driving cars, right? It's a confined area, risk is lower. You can do things, and there are. I have colleagues in Japan, actually in Tokyo Tech. They have a self-driving car. It's not doing day-to-day operations, but they run it sometimes on the campus for certain small, use cases, and it works fine. With the communication works well. I mean, they're developing the communication technology now. 6G could help again because we can potentially improve reliability, and that's something we're hoping can happen. But I mean, the biggest issue is not really communication. I think communication can potentially be resolved. It's more other things that come into the picture.
So maybe something like buses or, reliable public transportation, something consistent
Yes,
might be the first use. I see.
exactly, exactly.
Okay, let's continue on with safety a little bit, both in terms of security, and then also physical safety. people get concerned as you get more energy in your signal that might start affecting people's bodies, things like that. So just yeah, security and health concerns, I suppose, that we have for
And
this.
I think when it comes to security, I think security is one of those areas which is it's always an issue, right? Because you
Mhm.
come up with something interesting, there's always a way for someone to use it in a different way, right? I mean, so there's always an issue like AI, for example. Let's say self-driving cars actually work, right? I mean, they're perfect, there's no issue. Someone may actually go in and play with those guardrails, and that was not an issue before because you were driving the car yourself. So there's new security and safety issues. So I think the more we go with communication forward, the more there are going to be security issues. We solve one and there's another that pops up. I think one of the ways we should, not just in communication, but in general sense, is to try to build security as much as possible within the design. Because oftentimes the way security works, even to this day, we deploy technology, see someone who broke it, and then we fix it, right? We don't build it from the beginning. So the more you build secure solutions from the beginning, the better you probably will be. Again, communication signals being first everywhere, second being transmitted over the electromagnetic signal spectrum means that people can tap into them, right? And there's a lot of what we call attack surfaces where someone can just disrupt what you're doing. So that's gonna stay there. I mean, we've made
Mhm.
headways, of course. I mean, 5G was more secure than its predecessors, but again, there are things that will always come into the picture. Now, when it comes to this health and safety concerns, I think there's two sides to that. First, 5G won't create COVID. I mean, that has nothing to do with it, right? So let's get
Mhm.
that
Yeah,
up.
sure.
But second, of course, these electromagnetic waves, especially as you put them closer to your body, right? You're putting it on your ear and so on, and you have these wearables. There could be some sort of health risk there. I am not a healthcare professional to talk to in specific about that, but I have seen in our community people looking at the impact of electromagnetic waves on the body and so on. I think we don't have significant evidence to say that no, there is a concrete health risk there. But also, we should not rule it out just because we haven't seen it yet, right? I mean, I think there should be more serious investigation to that area. And again, for better or for worse, all these misinformation that happened about 5G and COVID, while that really was nonsense, it did shed a light about the possibility of having serious studies on what are the
Wow.
impact of frequency waves on the human body. They're not going to give you a virus, but there could be other things that we don't know about. And there has been some people studying it, I think more so in Europe than in the US. I'm not sure why. But I've seen more studies coming out of Europe and actually, the Middle East and other regions. Some of them are serious studies. I mean, I don't think they got to anything conclusive, but they're, for example, measuring where is where are the signals concentrated on the body, right? So we know better where it is and so on. What comes out of that, I don't know at this point, but I think it's worthy of investigation, definitely.
Yeah, I think that one's like there's definitely reasons to think that it's very safe, right? It's pretty low power, it's non-ionizing radiation. So there's good reasons to think that. But then things like chemicals that are relatively safe for us, and then we use a lot of it. And once the environment becomes inundated with it, it kind of changes things and the way our body
Exactly.
reacts a little bit.
So
So
the status quo is to say, I mean, there's very little evidence that it will do anything, right? I mean,
yeah.
most likely it's still no issues at all. I mean, think about it. We've been using phones for decades, and there shouldn't be an issue. But it's worthy to investigate it as it proliferates more. I mean, of course, you put VR glasses on your head and things of that sort. It's good to see if there is anything coming out of that, but it needs serious studies, not speculation, right? So.
Mhm. So I usually finish things with what problems do you think are important to work on your field? I know we talked already about a lot of the speculative technology. What's sort of something that you would like to see people working on that you think might unlock or really, change this field?
Yeah, I think if we want to have a real paradigm shift and looking really ahead in the future, I think there should be a true convergence of next generation communication systems with next generation AI. What we're doing with AI today is good, but it's more of we get something off the shelf from the experts in AI, we slap it somewhere, it works better, we do some testing on it, and maybe we find a use case. But as I mentioned early on, that eventually the technologies we work on in communication will get to a point where they're only going to give us so much because we're going to deplete almost all the possibilities there. And AI gives you a little bit, if you think of a different dimension to play with, the more you can get to like advanced AI, like more intelligent AI that reduces the amount of data you need because we don't need a lot of we don't have a lot of data often available in communication systems. So I think the intersection of the two, looking at it more seriously, especially given the drive in the AI community now to go towards what they call artificial general intelligence, AGI. And again, the term is a little bit loaded because there is no general intelligence even with humans, right? But let's say it's an AI algorithm that can not just repeat what it saw in the data, like what ChatGPT and so on do, but actually come up with some conclusions, right? Do some sort of reasoning the way we do. I think that is important for communications because if I am able to have a brain, so to speak, in the network that actually can make some deductions, it can help me plan the network better. And I think the breakthrough may come from there, the significant breakthrough. That's not discounting what we're doing now and not discounting the fact that, yeah, 6G probably will be successful. We'll see some cool applications and so on. And that will be great. But if we want to really change the field, I think we should look around, what does communication networks give AGI and what does AGI give communication networks?
Okay. You made it sound like we talked about earlier how we're kind of running up against limits of physics. It
Yeah,
almost seems like we're running up against the limit of human capacity to solve these problems.
exactly. Exactly.
Okay. Is there anything else that's exciting for you, interesting you are working on, or your colleagues, something you think we should look for relatively soon and give a time scale for, some of these things that we've been talking about?
Yeah, I think this idea of digital, what we call a digital twin, which is really twinning a physical system and creating a digital replica of it, like a digital replica of a car. I think this is an exciting technology. We're working on it, and it's, I mean, relatively as soon as we can, we will see things. I mean, some companies are starting to roll out things. I think it's a cool application. It's an interesting way to be able to test a lot of things. For example, if I'm, let's say, creating a twin of a car, I can, in the twin, in this quote unquote, it's not just a simulator, it just does more because it can talk back and forth to the car. But in this twin, I can take the car off the cliff and see what happens without affecting the real, right? So I can come up these make-believe scenarios to better understand what should I update in my system. I think it's an exciting technology. It has both short-term and long-term applications. And I think that's something I'm very excited about these days.
Okay, cool. Uh, that's all my questions. Thank you so much.
All right. No, I just want to thank you. It was a pleasure to talk to you.
Great. Yeah, you helped me a lot, actually. I'm always skeptical of stuff like this, and this is like, oh, it's making sense to me now. And hopefully that was communicated well in
I think
this
so.
conversation. So.